I wanted to talk about something that Oren said earlier. It was that you guys have at Intel, you have verification IP that's coming from within the company, from external vendors perhaps. And you mentioned to me once that you've got your designers actually doing the verification by consuming this IP from across the company.
Right. So I think like many people in the panel mentioned, I mean, the lines have blurred a lot. I mean, it used to be you've been a design engineer, you're doing design, you're doing RTL coding, or that was your job. You're done with that. You run some tests, you're done. You give it to the verification team, and they'll run it for you and find your bugs. That's not the case anymore. Basically, I would say 70–80% of your work is verification, whether it's through formal tools, structural tools, and running the simulations. The verification team primarily focused on building the verification environment, stitching together the verification IPs, and enabling designers to do verification. So that's just a fact of life.
Would you say that verification engineers are often skilled at finding out ways to break a design simply by not knowing how it works internally?
Yes, but and it goes back to your previous question. I mean, in an environment, and I'm from the SOC side, so an environment where everything is an IP, whether it's coming from another internal team or from an external provider, that comes with the verification IP. So the intelligence or the knowledge about what this IP is supposed to do is in the verification IP. The integration and enabling it, yeah, that's the verification team task. Running the design in the context in the scenario, that's actually done most of the time by the design team, and the lines are yeah, it's basically more on the design team, and the verification enablement is on the verification team. One more comment about IPs, the trend of basically SOC, which is a large number of IPs that are being integrated together, calls for more standardization and more common languages and being able to work with different languages in the same environment. One example we're using for all register, config registers, fuses, tap registers, we're using system RDL. So that's something that basically abstracts for us those descriptions. It captures all the specification, and from system RDL, we generate all the different formats. That has been a major improvement for us, and again, the knowledge of the spec coming from the IP team, where the SOC basically gets that knowledge through that format. And another aspect is coverage. I mean, if I could get, and in many cases I can, coverage database from those IPs, whether it's run before in simulation or it was done through static tools, formal tools, and so on, then I can also build up my coverage at SOC much faster. And I think going back to the discussion about formal tools, structural tools, and so on, that's something that is really missing right now, especially from the structural and formal tools. We can, unless they're generating assertions that we can write cover statements on them, we really need to guess or still have to go to our 100% coverage goal. If I could catch those assignment execution or block enables or undriven logic, the type of things that John was talking about, and that could also build into my coverage database through, let's say, something like QCIS, right? Then I don't need to repeat those tests. I think that's a major gap that we see right now with those tools. However, I do agree with Gary and with the rest of the speakers that this seems to be the sweet spot for formal verification. I mean, those apps, CDC, X propagation, low power verification, DFT. I mean, wherever you can constrain the problem and say, okay, here's a tool, it will check that area, and somebody without a PhD in formal verification could run it. That's the sweet spot.
Well, so for companies like mine where we sort of develop our IP in-house, it tends to be that the designs themselves actually mature along with the environment. And so, trying to provide a formal analysis early on in the project, as Dr. Goodenough was saying, sort of just proves that the whole design is incomplete. There's a point in time where it behooves you to start running these formal checks. Too early, and you're just proving that it's incomplete. Too late, and then you're finding bugs that are more expensive. Is there a particular point in time where you think starting to apply these techniques is worthwhile? Is there a point that's too early, a point that's too late?
Difficult question to answer that. And we often have this with our engineering teams where there's resistance to using a new technology. When you apply formal, you're right. If you apply it too late and you've already found the bug in simulation, then the formal technique has zero value to you because you've already found the bug. But if you run it early, then you found something that you didn't have to spend simulation cycles on. I'm sharing with the room here, one of the things I struggle with at the moment is finding some objective metrics that actually tell me when the right time to run it is, because at the moment it does seem to be somewhat down to a designer's preference as to their order of attack, and there isn't frankly a right or wrong answer. I think running formal early in some of the bring up activities, we've seen value in pulling bug curves forwards simply because the design ends up being slightly better structured before it goes to sort of bulk simulation verification. But beyond that, I think I don't have any data to back anything up.
Please.
I've got two comments here. I mean, I definitely agree that there's certainly applications, formal applications that can be run early. I mean, X applications and usually want to clean out this type of bugs. But I want to comment that the problem is not unique to formal in this respect. And for example, if you're you got to make the decision, when do I start gathering coverage? It's the same problem there in dynamic. You don't want to be gathering coverage too soon, otherwise you're going to have to toss all that out. So we have to make these decisions throughout the whole end-to-end functional verification process.
Absolutely.
So there may be another sort of bit of a nuance to this question and answer, and that is that there are things you can do with formal and static analysis that maybe simulation is not good for. So, for example, CDC and complex corner case control checking and so on. So simulation is going to find it pretty hard to figure out those kind of bugs in your design. And so it's not a question of early or not. It's basically that you have to use static techniques and a holistic solution for some of these kind of problems. And there are other places where simulation could have found the bug, and you're just making it easier on the verification engineer by finding those early. And I think that's where some of that the question that you asked needs to be answered. So I think that different companies find customize the process and figure out where in their process it makes sense to do this. And also something like X management, static analysis, it helps to improve the simulation productivity. So it's not a question of finding the bug early, it's a question of doing enough upfront in terms of the optimism analysis, pessimism analysis, and sort of redoing your RTL to make sure those kind of effects don't come into in simulation. In some sense, you're improving the verification engineer's productivity. So there are nuances to that question. Yeah.
So we're asking our designers now to not only do design and the synthesis and the timing, we also want them to do the lint, which they've historically been responsible for. We want them to analyze the code coverage. We want them to do CDC and X in static methods. Are there any others that we think that Mr. Smith?
Yeah, debug has always been.
Well, sure.
That's where one of the mistakes we made in the past was when we started building these verification teams. I mean, back in my day, the designers did design and verification, and there was a small, 1, 2, maybe 3 guys that did regression testing. And then when that team started growing into a verification team, one of the big mistakes we made was we drew this line, put a wall between the two. And that's, that has not helped us at all. In fact, even worse, what we did was outsourcing and outshoring, and that most everybody understands now is a really bad idea. And so that's all being reversed. And you really need the verification team in close proximity to the design team, plus the fact you're pushing more and more of of the verification problem onto where it traditionally belonged was the design engineer. I mean, so this isn't new. We're just going back to the way that really worked and getting rid of some bad practices. So yeah, debug has always been the designer's issue. Now, there are some verification teams that find the bugs and then hand them off to the design team. The design team has to fix it. And as far as when you start, I think what we're starting to see, and we're going to see in the fairly near future, is that engineers are going to start understanding when you use these tools. So it's going to be the gut feel for how the design is progressing before she starts doing verification or using verification tools to help him design his system. And then in platform-based, multi-platform-based design, the one thing you've got is that each of those platforms used in a design really is an endpoint in itself. They're a subsystem. So at that point, you can use all the verification tricks that you have in your bag because you have a complete sub-design. And then, of course, the assembly part later on has another verification problem that we're just starting to address.
Yeah, I think there's a key thing that designers can do, and we call it design. There's design for verification, which is just actually a proxy for good design practices. Don't have messy interfaces, instrument your design. But then there's design to help subsequent verification, which is where things like putting instrumentation in to help integration level debug becomes critical. You know, we quite often find the critical path is a system level bug running on an emulator late in a project. And you walk into the room and you see the guys sitting there scratching their heads. No, they're not the IP designers. They may have the IP designer sat there, but what you need is a way in which the IP designer can look at the design and the guy running a very advanced applications level payload can look at the same design running, and they can each see their view of it and then figure out what's wrong together. So we put a lot of emphasis on trying to put together debug environments which give different levels of visibility depending on who you are. Because certainly if you put a waveform viewer in front of a software guy who's dealing with a Linux kernel, he will run out of the door. And similarly, if you have the guy who's in the RTL, he doesn't want to sit looking at a source line assembly level debugger stepping through an operating system, but you need to be able to quickly switch between those views when you're debugging a problem. And the designers can do a lot to instrument their designs to provide, we use the term finger pointing IP or finger pointing assertions to go, well, I don't know what went wrong, but it's probably over there because I'm okay. And to try to really collapse down the time it takes to not necessarily solve a bug, but to triage where the problem is. Is it in the software? Is it in the test bench? Is it in the IP block? Is it in the way it's been integrated? And that's really the critical, ends up being the critical path on certainly a lot of our projects and a lot of our customers' SOCs.
Well, another thing I wanted to ask was, can somebody please explain to me what assertion synthesis is? Where is that tool being used?
Just another comment about debug. I think that just to cover on that, I think it's one of the biggest, at least in our side, the biggest gaps right now in terms of verification tools and environments. John mentioned triage. I think triage of we're getting bugs. Where is it coming from? The hardware, the software, which parts of the design, which IP? That takes days and days to just get to the root cause. System Verilog test benches. Most debuggers are not handling them in a nice way. I see wide acceptance to that. I think we mentioned software and hardware linkage. So just to clarify, most of the debug and the verification is done in a completely different, teams, tools, environments, hardware and software. I think the linkage has to be there, and again, big gap in terms of technologies and tools. something that we've recently started to look at, and it's also part of debug. How do you link this specification, which potentially coming from a higher level abstraction, to the actual design code that you're debugging? So if you could see what is the actual transaction that is failing in your high level modeling, and how is this linked to the specific X that you see, or checker that failed, and so on. All those are they're done by verification people, design people, but there are big gaps in terms of the tools and the environments.
Yeah.
Well, I think we're asking a lot of our designers, aren't we? We're asking them to have a very varied set of skills at this point. They often tend to think in terms of RTL, in terms of timing, and we're sort of asking them to take on a little bit more knowledge of the software space. We started this with assertions many years ago, and that's a whole skill set unto itself. Are they also going to be well, for example, when we run a simulation that fails, the verification engineer usually finds that it's a problem in the environment. Are we first asking the designer to triage that and try to take it into the environment, or no. Where do we start?
No, you're asking the designer to help the guy who's running that environment to go, the problem wasn't in the IP. And I think there are some, and it really just boils down to, rather than saying assertions, again, assertions is a technology. Assertions are a technology that let you basically do online documentation for your IP in a simulation or emulation environment. If you view them that way, you can kind of go, as a designer, my responsibility is to provide an executable data book that you're not doing anything dumb. Hey, wait a minute, guy, you just fired 6 transactions at me, I can only take 5, and my FIFO's just overflowed. Tell them that. Don't let them have to figure it out by mining down through waveforms. I think it's that sort of, if you were taking a technical reference manual for any product, you would actually have somewhere documented in there, by the way, be careful, don't, the FIFO's only five entries deep. Quite often at a system level, the guys who are dealing with that don't know, have no clue. They've got a pile of manuals sat next to them. That's where the designers can help them. I don't think you're asking the designers to be aware of the integration environments that their IP is going into, and you need the methodologists to give them guidelines on how they need to instrument their designs. But it's really just, it's not that they're learning a new skill, they're just documenting their design in a different way.
So we're talking about hardware, software. Does a hardware engineer need to become software experts into verification? No. What's needed is a more systematic approach in terms of the verification process, and we're seeing that emerge. For example, one of the steps in there is before we even get into any sort of serious hardware-software validation, is to ensure that the embedded processors can talk to the CSRs within the various IP blocks. I mean, you build up your process that the sooner you can find these bugs, the cheaper it is. If you just go all the way, let's integrate all the hardware and software, you're hopelessly lost. You will never have a big enough team.
I think that's going both ways too, because the software guys are having to learn more about hardware, especially in multi-processor designs. So it's the solid line that we had for years and years and years between hardware and software has been breaking down, and in a good design team, you'll find that the software guys have at least a first order of magnitude knowledge of hardware, and vice versa. The hardware guys have a first order magnitude of software, which is probably easier for the hardware guys because they are writing software when they're writing RTL. These software guys are in deep trouble right now because all of a sudden they have to worry about power. And that's just really throwing them for a loop.
So just one more point, that at the end of the day, it's not an exercise in perfection. It's sort of a best effort exercise. So any processes that you put in place in which designers, they scaffold the block with constraints so that anything that violates those constraints is obvious to the verification engineer. and anything that you can do in terms of modeling the software, any sort of abstractions that the designer can provide to the verification engineer to speed up the process and so on. All of this sort of contributes in a sort of cumulative manner. And there is, I think, a lot of low-hanging fruit, both combining the separation of the verification concerns and leveraging that in debug analysis and all of that, and focusing the verification planning on the system level issues and so on. And all of that is coming together, and it's a best effort exercise, and I think the trend is in the right direction. So.